Well, welcome back, everybody. For a moment, I thought I was going to be the only one here. But I hope everyone's doing okay. I will continue with the chapter that we ended up with. Any questions before I proceed? What I want to do is finish chapter 7 and then jump into 8. 8's pretty short, and maybe jump into 9 for a little bit. Okay. I just sent an email, a quick note. I sent an email to everybody in this class. I've uploaded some files that will help you with respect to the nomenclature, which is actually chapter 8 coming up. So there are a couple of files that help you with the naming and help you out with that nomenclature exam. Now remember, the reason I put the grades, if you've not done it or you've not reached the 80%, which is required by the SCC chemistry department to be considered a passing grade. The reason it's set to 0 now early in the semester is because in the past, we waited toward the end of the semester. And what happens is Canvas, if you don't do an exam or anything, any assignment, that grade is not posted in your overall. So students were getting kind of misleaded with respect to their grade. Now, the moment I put in a 0 toward the end of the semester, for some people, if you were on the border, the grade just dropped drastically. And then, they were scrambling to hurry up and do that exam, that quiz within given the time constraints. Normally the last week of the semester, and it was quite stressful for a lot of students. So to prevent all that, I put the 0 in now early, like 1:30 into the semester. And so now you know what effect that 10% of the nomenclature has on your overall grade. You have an unlimited attempts. Yes, the due date is the last day of the exam, but don't take that literally. Practice, do it, do some of it. I go in there and I check because some of the questions I do give credit. So I go in every attempt you make, I go in there and I give you credit for some things that Canvas missed or something. I'm trying to update that exam. That exam was created by someone else. And so I've been fixing it as we proceed. So though you may do like a 75, I go in there and check it. And I give you credit for something. All the questions are worth, there's 20 questions for 5 points a piece, I believe, yeah. So that'd be enough to get you at that 80. Now, if you're not happy at that 80, you can continue doing more and more attempts until you go on and you're happy with whatever grade you want. Okay, I've had students that have done at least 50 plus attempts, and because they're trying to make it 100, and I'm like, okay, go for it. Okay, so any questions about that nomenclature? Everybody understands, why there's a 0 in there right now. Okay, and even though I think it's December the 18th, which is our last day of class, is the due date. Please don't wait until that. Now, on the converse to that is this: if you are in that grade, whatever grade you have, and you're happy with it, and that 10% doesn't do an effect, it doesn't affect your grade one way or the other, that's your decision. And should I continue with it or just leave it alone? Okay. That's your decision, obviously. This is your class, you pay for it, your money. Okay. All right. Any questions about that? No? All right. Well, let us continue with where we ended up, and we had just finished this particular page where we were doing Lewis dot structures. Now we did Lewis dot structures on the atoms, okay, and that was pretty straightforward. I went too far, sorry about that. And the atoms, it simply only for the A elements is basically how many valence electrons they have, and then put a dot represent how many valence electrons they have. Straightforward with respect to the atoms. Now, we start making compounds, right? We put in the atoms together to start making structures and so forth. And this is where we ended up with, or started to do, is Lewis dot structures, okay? So we utilize the number of valence electrons that all of the elements bring to the table, if you will. We count them all up. And you should always have a number that is divisible by 2. Because what I do is I take those valence electrons and I divide by 2 to give me a number of pairs. Because it's easier for me, that's my own preference, to work with pairs. And I just draw a line to represent 2 electrons, a pair of electrons. And, you know, otherwise, if you do all dots, that's up to you. You know, sometimes you got 32 valence electrons. That's a lot of dots to keep track of. And so once you tally up all the valence electrons, that is what you got to work with. You cannot add more or subtract it because that's defined by the number of atoms and what type of atoms are brought to the structure. And so we make those valence electrons work. You're always told who the central atom is. We'll learn that normally you have a central atom, which will be identified either by bold because its symbol is in bold, or it's underscored, or you'll be told that element X is the central atom. That tells you that everything else that you see in that structure is bonded to the central atom. And we can very quickly draw a line that represents a pair and then attach all the other atoms to the central atom, okay? And that accounts for, you know, you can start, you know, you got to keep an inventory of the valence electrons or the pairs that you have to work with. And so if I got 10 pairs to work with to begin with, I make 4 bonds for whatever I'm making. So I just subtract it from my 10. That means I got, you know, 6 pairs to work with. I got to put them someplace, okay? So I start putting those other electrons onto other atoms. Hydrogen, if you recall, has a duet law, or duet rule with respect to its octet, okay? Because hydrogen will always only have 1 bond attached to it. That's it. So you can't put any more hydrogens on there. Excuse me, lone pair of electrons on the hydrogen. Once you made that pair, you're done, which is good. You know, you can forget about it once you attach the hydrogen. That means the other atoms now, you can place whatever excess pair you have onto whichever atoms you want, okay? But still maintain as you go along the number of valence electrons that you calculate, okay? At that time, when you put all the valence electrons that you calculate onto the atoms, sometimes everything works out, everybody's octet is fulfilled, sometimes it's not. And what you do with the electrons that you have, you start creating double bonds and triple bonds until such time that everybody has 8 electrons around it. The octet is fulfilled for everybody. Once you have that done, identify on the central atom any bonded pair, the number of bonded pair, and the number of lone pair. Lone pair are electrons that are on the central atom that are not bonded to anything. They're just sitting on the central atom. And we want to know that because from that information, we're going to generate a general formula where A represents the central atom, whatever it may be. B represents all of the atoms, and they don't have to be the same, they can be different. All of the atoms that are bonded to the central atom, okay, bonded to the central atom. And E represents any lone pair of electrons that are on the central atom. So I put a subscript X and Y because they represent numbers that you're going to determine. With that information, I'm rehashing what we did, so do refresh your memory because you know it's been a week now. You go to the shapes table, okay? And you see the first column here gives you the general formula that you have generated from the Lewis dot structure that you created, okay? And with that information, that general formula, now you know the molecular geometry of that compound. And then you also know the name of the shape of that geometry, and then the particular bond angle associated with that geometry. Our most common geometry in nature, it's quite a bit. The AB4 is the tetrahedral. You can see this model in the center, the geometry here, kind of trying to generate a three-dimensional model of what it looks like. And that has a particular bond angle of 109.5, okay? Remember, these bonds right here, these bonds here are electrons. And so they want to repel from any other electrons. So in this configuration, when there are four bonds to the central atom, these bonds are going to put themselves in the position so they're as far away from other electrons out there. And that's the configuration that is generated, the tetrahedral, okay? All right. Let's go back. And so we did an example of H2O. H2O has a total of 8 electrons, 8 valence electrons, okay? We know that oxygen is a central atom, and we can very quickly bond the 2 hydrogens, which takes care of, we got 4 pair, 8 valence electrons or 4 pair. That takes care of 2 pair, and then the other 2 pair of electrons, the only place they can go on is on the oxygen. And we check the octet / duet for a hydrogen, and everybody's happy here, okay? After we're done, we identify the general formula. We have A, which is the oxygen, okay? B, which represents the 2 hydrogens, so we get a subscript 2. And then on the central atom, we do have some lone pair of electrons, or non-bonded pair. So we do have an E. Specifically, we have an E subscript 2 because there are 2 pair of electrons. So that is our general formula. That is the information that we then go to the shapes table. And we look for AB2E2, which is the last entry down here in the bottom. Okay. Right here. And that is the configuration, the geometry. It has a specific name, bent. And that bond angle between the hydrogens and the central atom is much less than 109. And the reason they're much less, and this is also true for anything, any lone pair on the central atom, is because these lone pair take up space. They're not bonded to anything. They're going to repel each other. And so they take up space, forcing whatever else is bonded to the central atom to kind of be crushed in. So that bond angle gets much less than 109. Our reference point normally is 109.5 for a lot of the molecules that are out there. And then you can see that's why we say it's less than 109.5, because not only does it have a single pair, there's actually 2 pair. And so that this should be more like much less than just less. But regardless, it's still less than 109.5. And it's due to those lone pairs. Those lone pairs have a big effect on the structure of the molecule, which then have an effect on the properties of the molecule. And then that has an effect on such things like boiling point, such things as surface tension. And those are the kind of things we're going to learn about, how to interpret their relative properties. Okay, so let's go back. We did all these here, okay? And this is where we stopped last week, but those are the structures of these molecules. Granted, you may not know what they are, but that's okay. You know what the atoms are. You can find them on the periodic table. You can find them on what group they're in. That would tell you how many valence electrons. You're told here which ones are the central atom because they're underscored. Okay, that means everything else is bonded to the central atom. And then we continue to adjust the pair of electrons around that molecule such that everybody now has 8 electrons around it. The octet is fulfilled. Now, this is the part that sometimes students have a little bit of a tough time grasping, and that is the sharing. Okay, if we look at the triple bond that's sitting right here, okay, we have a total of 6 electrons in that triple bond. Remember, that line represents two pairs, so there's a total of 6 electrons. Well, those 6 electrons are being shared with the nitrogen and with the carbon, okay? And so they can be counted to both the carbon and the nitrogen. So when you are counting electrons around a particular atom, you know, one way to look at it is just simply kind of just isolate. Let me draw a different color here. Okay, let's just. Okay, and so I just draw a circle around the nitrogen, and I count all of the pairs slash dots around the nitrogen. And there are 8 around the nitrogen. 6 of them are shared with the carbon, but they count toward the nitrogen also. And 2 of them are a lone pair on the nitrogen. Okay, they're on the nitrogen themselves, not on the carbon. And when I look at carbon itself, I do the same thing. Okay, and so I got carbon here. Again, with nitrogen, it is sharing 6 electrons. They're being shared. We're going to talk about equal sharing and unequal sharing here in a bit. And the other 2 are being shared with hydrogen. And so there is a total of 8 electrons around carbon. 6 of them shared with the nitrogen, 2 of them shared with the hydrogen. And then finally, we look at the hydrogen. And the hydrogen has a pair around it. And hydrogen, as we stated, its rule is a duet, so there it's happy. So in this case, everybody's happy. There's 8 electrons or 2 electrons, depending who you are, around the atom. We still have 1, 2, 3, 4, 5 pair, or a total of 10 valence electrons, because that is what we calculated, okay? We calculated here 10 valence electrons or 5 pair. And we still have 5 pair, 1, 2, 3, 4, and 5. And so when you're done with the structure, do an inventory, make sure you still have the number of electrons that you calculated with, okay? And this is true for everything else. If you look at this one we did earlier, we got carbon in the center. It's got 6 electrons that are shared with 3 different fluorides, and 2 of them shared with the hydrogen. Therefore, you got 8 around it. If you look at each individual fluoride, there are 8 around it. 2 of the electrons are being shared with the carbon, and the other 6 are on the fluorides. They're lone pair on the fluorides, okay? And we can continue all the way around through all of them. Everybody has the octet fulfilled, and that's the structure. From this information, we then developed the general formula, and this was AB4, okay? This one would be AB2. Also, this one is AB2. And then we got here with AB3E. Notice the different general formulas that each molecule has. That information then is utilized using the shape table, which then gives us the geometry, which then gives us the name which then also gives us the bond angle, okay? The bond angle here with what is bonded to the central atom, okay? So you see how we take that information from the periodic table with respect to valence electrons. We learn about the atoms, we learn about especially the A elements, what group they're in, which tells us how many valence electrons they have, which tells us if they're metals, they're going to lose those valence electrons and become a positive cation. And depending on the group, we'll either have a 1, 2, or 3 positive charge, okay? If they're nonmetals, they're going to gain electrons, which then tells us whether they're going to have a -3, -2, or -1 charge for the nonmetals, from that information. So we gain that from the periodic table. We also gain how many valence electrons they have. So then we can put them together to start putting structures together, okay? All right, let's clear this up a little bit and move on finally to where we left off. We did talk about that. And this is just a summary of the HCN and what we did. Now, we're going to talk about doing the same thing we just did, Lewis-Dot structures, or we just did neutral compounds. Here, we're going to now talk about using drawing Lewis-Dot structures for polyatomic ions. Well, let me refresh your memory. Some of the common polyatomic ions that we utilize are on your periodic table. In the bottom left corner, you'll see a little table. It says most common polyatomic ions. Now, the majority of these are covalent compounds, okay? But due to the nature of the beast of these covalent compounds, they actually have charges because they are ions. Now, they're called polyatomic ions because they come together as a packet, all right? They are a packet. We don't separate them. And they even have their own specific name. For example, let's take a look at this one. Okay, we have nitrogen, which has 3 oxygens bonded to nitrogen. And the whole thing, the whole unit has a negative charge because it is an ion, specifically an anion. And it has its own specific name. So this one is called nitrate. Notice the suffix ATE. Let's take a look at this. Nitrogen by N, we know is simply, its name is nitrogen, okay? Now, when nitrogen by itself, nothing bonded to it, becomes an ion, it is in group 5, it will pick up 3 electrons and has a -3 charge, right? Okay, you can see that's a -3, and its name gets changed to nitride, IDE. So you have nitrogen, the element, nitride, the ion of the element, gaining 3 electrons, and then you have scenarios where the nitrogen is bonded to oxygens, in this case specifically 3 oxygens, and it's an ion, and it is called nitrate. Now, if you remove one of the oxygens, now you have 2 of them, it is called nitrite, excuse me. So you have nitrogen, nitride, IDE, nitrate, anytime you hear the ATE or the ITE, but you got Ni for nitrogen, that means that there's oxygens bonded to that nitrogen. So there's 4 different names that you have to be familiar with, okay? Because the same is true for sulfur. We have S, which is sulfur. Yeah, sulfur is in group 6, so it will become sulfide when it becomes an ion. Notice it's just the element itself. But there's also sulfur bonded to oxygens, specifically 4 of them, and it has an overall -2 charge, and that becomes sulfate. And then we have, there's 3 oxygens instead of 4, it's called sulfite. Now, when we get into the nomenclature chapter, the next one, this is related to what I sent you with respect to naming a variety of different compounds and how we use the periodic table to help you to determine which one do I have, the ite, and then we talk about hypo and so forth. It sounds like a little complicated, but there is a systematic approach to go to get the naming straight. Okay, we'll get to that. But the main point here is that these are units, packets that we keep together. We don't separate them together. If we ever need to add more than 1 nitrate, and we're going to learn why we need to do that, but if we ever need to add more than 1 nitrate, we actually put a parentheses around it, and then we put a subscript X, where X can be 2 or plus, 2 greater than 2, 2, 3, 4, whatever you need. We keep in mind that each one is a -1 unit. We don't change it, and it has its name that goes with it. Okay. Now, what we're going to do is just like we did for the neutral compounds, we're going to create Lewis dot structures for these polyatomic ions. And the procedure is exactly the same, except for one difference. That one difference depends on whether that polyatomic ion has a positive charge or a negative charge. Okay. If that polyatomic ion is a negative, and you saw from the table, the vast majority of them are negative, we're going to have to add a number that corresponds to its charge to the final tally of our valence electrons. So we add a number, whatever the charge may be. If it's a -1, then we add 1. It's a -3, we add 3 to the tally of our valence electrons. If it's a cation, positive in that polyatomic ion table, there's only 1, that was an ammonia. What we do is we subtract a number from the tally that we have. Okay. All right. So once we're done and we come up with a structure like we did with the neutral species, we then put a bracket around the formula, and then we put the charge, or whatever that charge may be, on the top right corner of that bracket. And we'll do an example here, okay? Let's try this one. This is the ammonium ion, okay? And we do no different than we have been doing with respect to the valence electrons. We have 1 nitrogen that brings in 5 valence electrons. Then there's 4 hydrogens that bring in 4. Okay. Notice if you forget to subtract or add, if you got 5 and 4, you add that up, you got a 9. Remember, that's a flag, because all of these valence electrons should be divisible by 2. So obviously 9 electrons is not divisible by 2. Okay. So then that should tell you, do I need to add or subtract? Okay. And now I know we're going to do both scenarios, and you're going to know which one is which here. All right, so it's a positive, it's a cation, so we're going to remove a 1. So now we have 8 electrons or 4 pair. Okay. Well, nitrogen is a central atom, not marked there, so we can very quickly write nitrogen and then put the 4 hydrogens on there. Okay, and that accounts for the 4 pair. And guess what? We got no more hydrogens to work, no more pair to work with. We're done. Is there 8 electrons around nitrogen? Yes, there is. Is there 2 around hydrogen? And the answer is yes. And so everybody's happy here. So now what we do, we put that bracket, okay, not a parentheses, but a bracket around the whole molecule. And then it's a plus, it's an ion, so we put the charge in the top right corner, okay? And that is what we present. Now, we can do a general formula here also, just like the neutral species. We got A and B4. That is their general formula. A is nitrogen, B is the 4 hydrogens around it. And so with this general formula, we go to the shapes table, and guess what? That's tetrahedral. So that shape in there is a tetrahedral shape with that bond angle at 109.5, okay? All right, so let's say, for example, instead of subtracting, you made the mistake of adding. And so you go 5, 4, and then you did a +1, okay? So that gives you what? 10, right? So that gives you 5 pair to work with. If I can emphasize here, if you added instead of subtracted. All right, so you got 5 pair. All right, so then you very quickly, like we just did, I'm going to put this in yellow, assuming we're dealing with 5 pair here, okay? And so we're dealing with 5 pair, at least that's what you think you did, or you have. And so you put nitrogen down like we just did, and then you put the 4 hydrogens like we just did. And now that takes care of 4 pair, you got 1 pair left. And you look at that 1 pair and you think, well, where can I put it? I can't put it on the hydrogens because they're full. And I can't put it in the nitrogen because we got 8 around it. And if I were to do this, what would be wrong with that picture? If I were to put a lone pair on this, what do you guys think is wrong with this picture I just drew? I got 4 hydrogens bonded, and then I put the extra pair on the nitrogen. Is there anything wrong with that picture? In yellow?
The nitrogen's not happy anymore because
Yeah.
Yeah.
Has how many?
10 instead of 8.
You got it, exactly. And so the fact that you got 1 pair left in your addition, your inventory, so to speak, and you got no place to put it, because you know that if I put it on the nitrogen, that gives me 10, and that violates the octet rule, that should tell you, maybe my mistake's right here, okay? All right, and the opposite would be true when we do an anion. We'll do that here in a second. If you, instead of adding a number, you subtract, you end up short. And no matter how I can make double and triple bonds, I don't have enough pairs to fulfill the octet on a lot of the atoms. So those are flags to tell you that someplace around here, the math was done incorrectly, okay? All right, let's clear this up. And so the structure is as follows. This general formula is AB4, okay? So that is for the cation. Well, let's do some more. Now, of course, these are unusual. We don't know what they are, but we'll learn them. The top is a bromate. We'll learn about those ions. But point is, the central atom is highlighted for you, so you know who the central atom is. And so all the other atoms are bonded to the central atom. And all of these are anions, okay? So the very top left is the bromate. We do what we normally do, add up the valence electrons. The bromine brings in 7. There are 3 oxygens, each one bringing in 6, so we have a total of 18 electrons. Now, another flag will be here. If I were to add those 2 numbers up, what do I get? I get 25, right? So that number is not divisible by 2. So I'm either going to add or subtract. Let's assume you did this correctly, and you added because you have a negative ion in that ion. So we tally that up. We got 26. We got 13 pair. 13 pair to work with. So we do what we've been doing. Br, bromine, is the central atom. We put that in there. Very quickly, we got 3 oxygens bonded to that central atom. And so I can very quickly put my 3 oxygens on there. And that takes care of 3 pair. So I can subtract from the 13 I got to work with. I got 10 pair to work with. That. And, you know, you can put them anywhere you want. So I stated, maybe I did or did not, but I tend to like to go on the outside atoms and put them all there and then work with that after I got them in there. So I got 10, so I'm going to start with any one of these. I'm going to just go 1, 2, and 3. I cannot add more than that, right? Because I got 8 around oxygen right now. So I move on to the next one. That's 3, 4, 5, and 6. Similar scenario. I got 4 pair all the way around that one. That's 6, 7, 8, and 9. So that took care of 9. So I got 1 pair left. I can't put them on the oxygens because they're happy. So the only logical place they may go, have to go, would be on the central atom. Now, 2 dots or line makes no difference. Okay, both represent the same thing. Check my octet. I got every 8 around the oxygen. I got 8 around the bromine. Everybody's happy. And so now I just put my bracket. Okay, it's got a negative charge, put my charge outside the bracket. Okay, my general formula, just like we did before, we got A, B, 3, and this time we got an E because we have a lone pair sitting here. Okay, so that would be AB3E. Now we go to the shapes table, AB3E, and there we go. AB3E, and there we are, right there. That is the shape, the general formula. That is the shape. That is the name, trigonopyramid, and the bond angle less than 109. Again, because the lone pair on the central atom is pushing the bonded pair down. Okay, because the lone pair takes up space. Here's something to put in long-term memory. Anytime you end up with a lone pair on the central atom, remember this, you have a polar compound, polar, okay? Because we're going to be talking about polar and non-polar, basically water-like and oil-like. So anytime you end up with a lone pair on that center atom, you got a polar molecule. And we'll learn more why that's the case here in a bit. All right, so let's go back to that, and there it is. Here's the structure that we come up with. Okay, let's try the sulfate, SO4 -2. That is a polyatomic ion that you'll find in the table. Okay, well, sulfur brings in 6 valence electrons, 4 oxygens, it's a total of 24, and then it's got a -2 charge, so we add +2. It gives us a total of 32 valence electrons or 16 pair, and then we proceed like we normal. You can see that the sulfur is the central atom, so we can very quickly write sulfur. There's 4 atoms bonded to the central atom, so we can go 1, 2, 3, and 4, bond the oxygens with a single bond. So that takes care of 4 bonded, 4 pair of electrons, and therefore we have a total of what, 2, right? 12. 2. All right, so now we just put them around the oxygens. Obviously here you can see that sulfur has 4 pair all around it already. So it's already following the octet rule. So we just simply go 1, 2, 3, 4, 5, and 6, 7, 8, 9, 10, 11, and guess what, 12. Check your inventory. We just did 12, 13, 14, 15, and 16. So we're good to go. We had 16. We ended up with 16. Okay, this is an ion. So we can Put the bracket as the -2 charge. Okay, we're good to go. Last thing to do, if necessary, is a general formula, which is AB4. A is sulfur, 4 oxygen, so we've got AB4, nothing on the central atom. No E's, obviously, here. And if you look that up on the shapes table, that becomes tetrahedral with the bond angle of 109.5. Okay, bond angle right there. Okay. And so the point here with ions, polyatomic ions, same as we doing. The only thing to remember is adding or subtracting the number depending as to the charge. Is it a cation or an anion? The last one is a cyanide. Recall that we did HCN. Okay, and here now it's an ion because that hydrogen's been removed. And so we got 1 carbon with 4, nitrogen with 5. It's got a negative charge. We're going to add 1, so we got a total of 5 pairs of valence electrons to work with. You really don't have a central atom here because it's only 2 guys here, 2 atoms. You pick each, anyone you can pick either one, doesn't make a difference. Okay, and then it's a matter of putting those electrons around them. And then like we did the HCN, we ended up doing a double bond and a triple bond. And here, this is what we got. We ended up with. And you see that there are 5 pair around it. So nothing was lost. It's a negative charge. And since there's only 2, automatically it's it's a linear species. They don't even have a general formula for it because you don't have a central atom. Okay, it's simply 2 atoms together, linear. Okay. With respect to this concept, any questions about this as far as the anions and the cations? Remember, you got to add or subtract depending on the time. But other than that, it's the same procedure as for the neutral. Right. Now, I've been stating that, you know, here's the bond angle, and whenever you got lone pairs like here, that tends to affect that bond angle right here because these lone pairs tend to take up a lot more space because remember, they got a negative charge. They're repelling each other. So they're in this orbit by themselves, not bonded to anything. And, you know, they're going to repel each other and resulting in whatever's bonded down here to be crunched in, which then affects, again, the properties of that compound. And that aspect is a model called the VSEPR. It basically says called the valence shell electron pair repulsion model. Okay, and all that means is the same what I just told you. Those lone pairs have great effect on the overall arrangement, 3-dimensional arrangement of the molecules, which then affect the properties of that compound and the effects, the properties of these compounds reacting or interacting with each other, which affects things like I stated, boiling point, surface tension, vapor pressure, and so forth. We're going to be at the point at the end, not here, but with time here, that we're going to be able to take a look at 2 molecules and do a relative comparison and say, okay, this one's going to be more soluble in water than this one. Or we could say, well, this one's going to be, has a higher boiling point than this one. We're going to have relative comparison. We can't do absolute, but we can do relative comparison. And it's all related to how these atoms are bonded together, which to determine, we need to do the Lewis dot structures on these things, which gives us the general formula, and then we can go on, but more on that. So this is the shape table. I've introduced this all along the ABE general formula. Central atom, B is whatever is bonded to the central atom. And E, remember, it's only the lone pairs on the central atom. We don't really care about the lone pairs on anything else, okay? Like these guys, like the sulfate. We got 3 lone pairs on the oxygens. That has no effect on what we're looking at. Only when there's on the central atom, like the bromate, there's lone pair on the central atom, okay? the one that's linear, anytime you have two species, like with the one we just did with the cyanide ion, it's simply linear. That's it. You got two things together. So all the diatomics are linear, okay? H2O2, etc. Another one that's linear is an AB2 model. A good example is carbon dioxide, okay? We did do carbon dioxide. We ended up making double bonds on each side of the carbons, which then results, because of the nature of the bees, to have a linear species, okay? Another one that is called trigonoplanar, we have A, which is a central atom, and then three atoms bonded around it. So if you look at this structure, it's called trigonoplanar. It's kind of flat, okay, with all of the three items, oxygen, hydrogens, all separated by 120 degrees. A good example there on the right side is what we call the space field model, to give you kind of a picture of what we think it looks like. This example is formaldehyde. You might be familiar with formaldehyde. If you ever had to dissect a pig in high school and this pig's been stored in a solution that formaldehyde is preservative. However, they don't use it so much now because it does have cancer-causing properties. Tetrahedral. Okay, that's AB4. Basically, again, the bonds, we got the model on the right. The dark center is the carbon and the white spheres are the hydrogen. In that bond, you can see that, remember, those are two electrons that are being shared. And so they're going to repel, all four of them are going to repel each other such that that's the formulation, that is the structure that they have, tetrahedral. A lot of the most common structure around 109.5. Then we have what's called the AB2, okay? AB2E, we call that the bent. Now, you would think that if we look at, let me write this, if we look at carbon dioxide, CO2 structure-wise, and we look at sulfur dioxide, you might think, oh, wait, similar structure, right? We had carbon dioxide that we came up with like this. Well, not necessarily, right? Because sulfur is on a different group, so it's bringing in more valence electrons than carbon is. The result is you end up with this particular structure with the lone pair here, and thinking that it would be similar to the trigonoplanar, like that one, but the problem is that there is a lone pair on the central atom, resulting in that bond angle being much less than 120, because again, as I stated, that lone pair takes up space and they tend to crunch this bond angle down. Second of all, don't mistake, because they look very similar. One atom, three atoms for carbon dioxide, three for sulfur dioxide. Don't think that they have the same structure. They don't, because they bring different valence electrons, number of valence electrons. So this is sulfur dioxide with the AB2E bent configuration. And with the lone pair on that central atom, you have a polar molecule. All right, here's another one. This is ammonia, NH3. We've all smelled ammonia. This is the structure that we have. And you have three hydrogens bonded to the nitrogen, but then you have a lone pair on the central atom. Again, that bond angle gets crushed in because that lone pair takes up more space, and it doesn't show it very well in the model there, but the lone pair will be like sit up in here, okay? So it'll be crunching this bond angle down here, less than 109.5. Again, this particular molecule has a lone pair on the central atom. We have a polar molecule here. you'll understand here why I'm stating this here, because eventually what we'll do is you'll be asked to, given the formula, determine the structure, and then from there, determine the polarity of that molecule, whether it's polar or non-polar. Okay. We'll elaborate that here in a bit. Water has the structure of, is an example of an AB2E2. E2 meaning that there are two pairs of lone pairs on the central atom, making it extremely polar. In fact, water is probably the most polar molecule there is. Okay, good old-fashioned water. All right, so summarize all this, given the molecule or given the polyatomic ion, be able to draw the Lewis dot structure, okay? And from that information, using the shapes, they will determine the shape and the bond angle. All right, so practice, there's a couple that you may want to try, pH 3 and ozone. That is the formula for ozone. There are 3 oxygen atoms. Obviously, you're bonded one of the oxygens in the central atom. So you can play with the valence electrons and see what kind of structure you come up with. Maybe next Friday, if you have a challenge with it, bring it to class and we can go over it. Okay. See if you can do those. All right, which brings us to what is called polarity. Okay, I just briefly touched it a little bit. What I need to do is this. Let me call up. There is a simulation on the course website. And let me pull it up. Okay. All right, let me do share. I'm going to the course website and I'm going to the modules. There, if you not had a chance, do look at them. These under the module called additional chemistry resources. There's another one here that 2 more I'm going to load up for you. But select the one is called molecule polarity. Okay. If you click on that, you where'd it go? You would send you to a course, a simulation. It's a website run by the University of Colorado. They have a variety of different simulations. Select the 2 atoms, okay, simulation. And what you have here is a model of, you got an A and B. All right. Now, right now, atom A and atom B have equal electronegativity, okay? Remember the property called electronegativity, or EN, not to be confused with ionization energy, okay? The electronegativity was a measure of an atom, the measure of the affinity of a bonded atom for electrons. And so when you have a bond, when you have one atom that has a greater affinity or greater electronegativity, that bond between them is skewed. Normally, a lot of bonds are equal sharing of that line between those 2 electrons. So here you got that dark bond between A and B. Right now, there's equal sharing, okay? Because they have, let's say, the same electronegativity. It's a tug of war. And right now, the 2 people doing the tug of war are equal. So there's no difference. Now watch what happens. 2 things. As the color changes to red, because B's electronegativity, I'm going to be sliding the scale. And you notice something as I slide the scale that B becomes redder in color. Okay. What that means is as the electronegativity of B increases, it tends to pull more electrons onto itself, resulting in A having less electrons. Okay. What that means is on A side, we create what is called a partial positive charge. That symbol that you see there is, let me try a different color. It's hard to see that. That symbol is called, it's a lowercase delta, but means partial. We use it to represent partial. Okay. Remember that in ionic compounds, we had a full-fledged charge. You know, if we looked at sodium chloride, we got a full-fledged on sodium and a full-fledged charge on the chloride. They came together like two magnets. With covalent compounds, that's not the case. They're sharing the electrons, so there is a physical bond between them. And sometimes there's equal sharing, but when there's unequal sharing, because the electronegativity in one of them is greater, we end up with a partial charge. So A has a partial positive charge. It has a positive character to it, okay? B has a partial negative charge, okay? What in effect we have created here, what's been created is what we call a dipole. Can anybody think of another example of a dipole? Can you think of an example offhand of something that could be classified as a dipole? Let me give you a hint. You're living on it right now. What do you think? The Earth. Does not the Earth have a North Pole and a South Pole? Hence a dipole, two poles, okay? The electronic device you're working with right now, if you're running off a battery, you have a dipole. In fact, even the electrical current's got is a charge. But anyway, you have a dipole if you're running off the battery. The battery has a plus and a negative, okay? So the result is this. You have, due to the electronegativity difference, a dipole is created. On one side, you have a partial negative side and a partial positive side. And what happens is there is an arrow called the dipole arrow that is created. The point of the arrow points to the most electronegative element, B in this case. And the back of the arrow, which generally has like a little plus sign to it, and that's what right here, points is on the A, that represents the partial positive. That has an effect too. If we put this thing, so we can adjust this, let me clear this. If we put an electrostatic field in here, I can move it around. And if I put electrostatic field, basically a plate with a positive and negative charge, guess what? That molecule gets lined up because of the respective charge that it has. Okay, partial charge. All right. Now notice what happens when I'm going to put the B on that amount of electronegativity. And if A has an equal amount of electronegativity, wow, look what happens. No more. Equal sharing, no dipole. Okay. So molecules that have the same atom bonded together, hence all the diatomics, are nonpolar. When you have a difference like this is called a, let me draw this. This is called a polar bond when you have a dipole, okay? When you don't have a dipole and both of them are the same, you have a non-polar bond, okay? So that's the difference between a polar bond and a non-polar bond. And the difference is the electronegativity in that bond. So all of your diatomics have non-polar bonds. Okay. All of the diatomics have non-polar bonds. Now, here's something else I want you to be aware of. Let's go back to the arrow. When we have a polar species, notice that arrow. That particular arrow, okay, that is, is what we call a vector. All right, it's what it is not important right now. Vector, excuse me, OR. A vector is something like this. It has magnitude and direction. All right, if I say to you, 20 miles, it means nothing, right? But if I say go 20 miles north, now you have a vector because you have the amount, the distance, the magnitude, and direction. The point is, the fact that it has directions, these vectors, these arrows can be added or subtracted just by graphically viewing them. So if I have an arrow going to the right, I have a vector going to the right of an X amount, okay, we'll just call it 5 units because that's the amount that arrow length represents. If I have another vector, arrow going in the opposite direction, also of 5 units, but because it's going into the left, it is going in the negative direction. So it's got a negative 5 units compared to the one on the right as a positive 5 units. And guess what? When those vectors go in opposite direction, they cancel out. So the net equals 0. If they were going in the same direction, both of them 5 and 5, then the net would be 10, okay? Now, the one we're interested in is when they go in opposite directions. Because if we look at carbon dioxide has a dipole. From the carbon to the oxygen, it's going to the right. And it's going to the left in the other direction. They both are carbon-oxygen bonds. They both have the same magnitude. Guess what? They cancel each other out. And when they cancel each other out, the net is 0. And even though they got polar bonds, they cancel each other out. And we end up with a non-polar molecule because the bonds canceled out. The polar bonds cancel out. Remember we saw that picture of the sulfur trioxide? Oh my God, a little bit different. Okay, had a lone pair sitting on there. Well, it's got a dipole going down in that direction and a dipole going in that direction. Okay, they don't cancel out because they're going in completely different directions. All right, so we end up with a polar molecule because the lone pair pushed that angle down, and that made it into what's the word? That made it so the dipole angles cancel each other out. Well, you might ask, well, how do I know which direction the arrow goes? Well, remember what we did with electronegativity? Here's the periodic table, okay? Somewhat. Here's fluorine, approximately right there, right? Fluorine was the most electronegative element on the periodic table. And that was our benchmark. Remember I stated that? And so when I want to do a compare and contrast as far as electronegativity, I've determined those two elements as I determine where their position is relative to fluorine on the periodic table. And so let's say I want to look at carbon and nitrogen, okay? Because they are bonded together. And I want to figure out which direction does that arrow go to? Well, I go to the periodic table. I notice that nitrogen is much closer to fluorine, okay? Nitrogen is much closer to fluorine. Therefore, that dipole is going to go from carbon to nitrogen. There'll be a partial negative there and a partial positive on the carbon, okay? And it's a polar molecule, polar bond. Okay, so to determine whether a molecule is polar, we first have to look at the bonds and determine whether they are polar or not. Because in general, when a molecule has all nonpolar bonds, we end up with a nonpolar molecule. In general, when a molecule has all polar bonds and they do not cancel out, we have a polar molecule. Okay. All right. I realize there's a lot of information here, but we're going to run through it again. So use this, kind of go through this, it'll help you out there, kind of grasp the concept of a polar bond, because polarity is going to be coming over and over and over again. Polarity is going to be is a big factor in chemistry. If it wasn't for a polar bond, it would be very difficult for us as organic chemists to synthesize anything. One of the problems of trying to take hydrocarbons to break those up is because there's no plus or negative charge. There's no polar bond in there that we can take advantage of, so we can break it up if we want to break up hydrocarbons or even put them together. We got to have an area that has a polar bond so we can come and react at that spot, because guess what? A polar bond has got a positive end and a negative end. And we can tap into that property to make other compounds. That's why we have, like, for example, antibiotics, or a variety of different antibiotics. Yes, some of them are extracted, but a lot of them are made. We synthesize them and we rely on the polarity and the polar bonds in there so we can make analogs. And those are compounds that are like the basic, like penicillin. We can make analogs of penicillin. Structurally, they're a little bit different, but the base structure is still the same of penicillin, for example. Anyway, polarity is very important. So let's go back to the all right, so when we have a covalent bond, when we talk about bond polarity, this is only true for covalent bonds. We have ionic bonds that are polar by default because we got a full positive and a full negative. Okay, where covalent bonds, we have a subset. Underneath that subset is this. Let me do it this way. On one side, we have ionic bonds. Okay, and that is for example, that is a metal and a non-metal combination. They come together due to electrostatic attraction because there is a full positive charge on the metal and a full negative charge on the non-metal. With respect to covalent, we have non-metal and non-metal, okay? But underneath the non-metal, we have a subset where we have a polar bond and a non-polar bond. Okay. When the elements that come together in a covalent bond are the same, we end up with a non-polar bond because those electrons are being shared equally. Okay. And as a general guideline to help you out, if you see like A is the general formula, A bonded to A, we got a nonpolar bond because A and A are both the same guy. Now, there's one exception to this. Anytime you see a carbon-hydrogen bond, you have a nonpolar bond, okay? Carbon-hydrogen bonds are a nonpolar bond. The reason they're nonpolar, even though they're different, is because with respect to electronegativity values, the carbon and the hydrogen are so similar, the difference is negligible, and therefore they're considered to be nonpolar. Case in point, a lot of oils, fatty acids and stuff like that have a lot of carbon-hydrogen bonds, and they don't readily dissolve in water, okay? We know that oil and water don't mix. Oil is a non-polar bonds involved in there. Water, very polar bonds. Okay, so that's the only exception for a non-polar bond to dissimilar atoms. So what that means is if I got A bonded to B, I don't have to think about it. It is a polar bond because I got two different atoms in depth, with the exception of carbon hydrogen, because I got two different atoms and automatically I have a polar bond. I need to figure out which direction it's going, and that's related to the electronegativity. Okay. All right, so that's what a polar bond is. Because in a polar bond, two different atoms, two different electronegativities, one of them is pulling an electron onto himself much greater than the other. Okay. And therefore we end up with a pole, just like a magnet, and just like the Earth, we got a North Pole and South Pole. In this case, we have a partial negative and a partial positive pole. Okay, clear this up. And that is where sometimes students have a challenge with. If they look at the molecule, you don't have to go look at, let me restate this. Every element has a electronegativity value. And it's not necessary to sit there and memorize or look up the electronegativity of every element in a bond. All you got to do is find it on the periodic table relative to fluorine to tell you that, well, point one, point two, when you have, let me give it to you in generic terms, and I can't overemphasize this. A, which I'm just generic compound, A bonded to A, okay, automatically, bam, non-polar bond. They're both the same, okay? Also include that in that list is a carbon-hydrogen bond. All that, combine all that, non-polar bond. When I have A bonded to B, which is a totally different species, different element, automatically polar bond. That's it. That's how simple it is. We don't have to put more thought into it, okay? Other than possibly remembering the carbon hydrogen. Yes, it's an AB example, but because of the electronegativity of each one, it's a nonpolar bond. Now the next question is, okay, which direction, who's got the partial negative and who's got the partial positive? Well, we find the position of A and B relative to fluorine. If it's fluorine, then it's a no-brainer. Automatically, it's going to fluorine. Why? Because fluoride, I should say, is the most electronegative element. We don't have to look at anything. Anytime you see fluoride, and let's say we have something like HF, well, automatically that dipole arrow is going in the direction of fluorine, okay? All right, if you see fluorine bonded to fluorine, they're both the same, okay? Dipole, all the diatomics are nonpolar, okay? No dipole involved there. All right, and now if this is a carbon-hydrogen bond, as I stated earlier, carbon-nitrogen bond, I should say, automatically it's A-B combination, it's a polar bond. Now the question is, all right, which direction does the arrow go to? I look for the direction, I look for the electronegativity, route the negativity of carbon nitrogen to fluoride, that is their position. Nitrogen is closer to fluorine. Therefore, the arrow in that bond goes in the direction of nitrogen. So nitrogen has a partial negative and carbon will have the partial positive. And there it is, okay? You don't have to look things up at all. All right. This is the question about electronegativity. We've just talked about. There's the trend that we talked about in a chapter ago, 2 chapters ago. Okay, fluorine is sitting there in the top right corner. Okay, that is the most electronegative. So all diatomic molecules are nonpolar, okay, because they have the same element. Also, if you're looking at a bond where you have carbon bonded to carbon, whatever, else is happening someplace else, we're not concerned. But if you're asked about that bond, that's a nonpolar bond. Why? Carbon and carbon are both the same element, okay? All right, so that's a nonpolar bond. The same would be true if we have molecules that nitrogen bonded to nitrogen and we have other things bonded to it. Yeah, that's a nonpolar bond because the elements are the same. At least for Chem 130. There is a slight difference, but we're not going to go into that. Carbon-hydrogen bond is considered as a nonpolar species. Okay, let me do this. I need to take a quick break. It's 2:16 right now. Let's come back at 2:30. Okay, and we'll continue. Okay, I am back. Excuse me. So anyway, we're trying to define what are nonpolar covalent bonds, okay? And as I stated, anything bonded with identical atoms is a non-polar covalent bond simply because the electronegativity between the two is the same. Additionally, carbon-hydrogen bond is considered as a non-polar bond. Right? Now, in the most Can you hear me okay? Anybody having trouble? I just got a note to say my connection was a little bad.
I can hear you.
Okay, thank you. All right. So most covalent bonds between two different nonmetals, one of the two atoms will hold the electrons more tightly, and that is related to the electronegativity. Again, I cannot emphasize going to the simulation that we just showed you to kind of help you understand and grasp what's going on here with this concept here. So if we look at carbon-oxygen bond, hydrogen chloride, sulfur and fluoride, silicon, nitrogen, they're all different elements, okay? And therefore, just by default, in that particular bond, it is a polar covalent bond, okay? Now, in the direction that that pole goes depends on the electronegativity, right? And we use the periodic table to help us out, knowing that fluorine is the most electronegative element, regardless if it's fluorine or fluoride, okay? Most of the time, as a bonded, then it's called fluoride. And we use, excuse me, that notation, the partial positive, the delta, lowercase delta positive and lowercase delta negative, to tell us that there is a partial positive and a partial negative charge, okay? And so if we look at the bottom, we got carbon fluoride bond. Automatically, fluoride's most electronegative. So obviously the arrow will go in the direction of the fluoride, and therefore the fluoride has the partial negative. In an oxygen-hydrogen bond, oxygen is way closer to fluorine. And so with respect to the comparison of hydrogen, which is in the far left side of the periodic table, oxygen is a lot more electronegative than hydrogen. Therefore, the arrow in this case goes from right to left with the partial negative on the oxygen. And then the bond between the phosphorus and chloride. Well, phosphorus and chloride are both on the same period, third energy level, but the chloride is right underneath the fluoride. So it has a higher electronegativity than the phosphorus. So the arrow goes from the direction of left to right, okay, left to right. All right, so obviously noble gases, they don't really have electronegativity. They're just happy where they're at, okay? Because they got their octet fulfilled. There's no bond being formed, no pulls, no nothing, okay? And fluoride, yep, stronger electronegativity. That's why they use fluoride with in your toothpaste. Supposedly, I don't know for sure that whatever bonds are being created or they do make it fairly strong, but fluoride has also been shown to cause other health issues. So that debate's been going on for years. You could be given an example of a bond and you're asked to write the delta notation and the polarity arrow for these bonds. So you got carbon, oxygen. You go look up on the periodic table the respective position of each element with respect to the fluoride, and you see that the oxygen is much closer to the fluoride, hence a higher electronegativity. As I stated, you can also go look up the electronegativity of each element. Each one does have a value, but it's not necessary. You just find this position on the periodic table relative to fluoride, and that tells you in what direction the arrow goes. So we got the partial negative on the side of the oxygen. Nitrogen fluoride, no brainer here. Why? Because fluoride is the most electronegative. Automatically goes from left to right. Oxygen, as we stated before, in this case, from right to left. Okay. And if it's written the other way, the arrow then just goes from left to right. Makes no difference, as long as it's pointing toward oxygen. Then we got the chloride and the carbon. Now, carbon is a lot less electronegative than the chloride. So the arrow in this case goes from right to left with the partial negative on the chloride side. And then we have the hydrogen carbon. You might think, going with different elements. No, remember, no dipole here because it's considered to be a nonpolar bond. All right, so question could be asked, okay, are these bonds ionic or are they polar covalent or non-polar covalent? All right, so first of all, you go back and refresh your memory. Is it ionic compound? An ionic bond means I got to deal with a metal and a non-metal. So bromine is not. Two non-metals, definitely a covalent species. Bromine. Second of all, the next step is, okay, is it polar or non-polar? Well, the fact that they're two of the same elements tells you that they are non-polar, okay? Non-polar. If we look at phosphorus and fluoride, two different elements, automatically polar species. Sodium and chloride. The fact that you got sodium, which means you got a metal, non-metal combination, sodium chloride, it's ionic, okay? No arrow there, because automatically, remember, it's an ionic bond. Sodium has a full-fledged positive charge in it. There's no partial there. And chloride has a full-fledged negative. And then obviously we got two, you might think, well, they're two, it's a diatomic because you got fluorine and bromine. However, they're different elements, okay? And therefore, yes, it is polar, okay? All right, so polarity itself is very important because it keeps coming over and over again. And as I stated, just think of it as a tug of war between the electrons in that bond. Some of them have an unequal tug of war and some of them have it equal, which affects the properties, okay? Which affects the properties and such things as whether a molecule is more soluble in water. We use as a reference point, water and oil, because water is polar, no questions asked. Most polar species there is. Polar bonds, polar molecule. Note the difference I'm saying. Polar bonds does not necessarily mean you have a polar molecule, okay? All right. And I use the example of carbon dioxide where that polar bonds cancel each other out because those arrows represent what we call vectors. They have direction and magnitude. And so if they're going to the right, and one's going to the left, one's going in the negative direction, one's going in the positive direction. And if they're lined up with each other, they cancel out, okay? I'll get some more examples here in a bit. So we take here, we might have a list of things where we say, is it ionic, polar, or non-polar? Well, we got sodium chloride. We've done this a number of times, you know, that is ionic, okay? It's an ionic bond, okay? Hydrochloric. Now, the thing about ionic bonds, refresh your memory on this. I mentioned to you, ionic bonds, when we place them in water, they will dissociate, okay? Some of these ionic bonds, all ionic bonds will dissociate in water. Some dissociate 100%, totally soluble. Others, not so much. Some of it still goes in solution, but they're still ionic and they still go a little bit into solution, okay? Now, I also stated that covalent bonds, normally when you place them in water, do not break apart. They stay intact. So carbon dioxide, we put that in water, does not break into the carbon and oxygen ions. They don't, they stay intact. The only example of covalent compounds that dissociate is this one here, HCl. Acids, we have a whole chapter on acids, chapter of acids and bases. That is the only example of a covalent compound that when placed in water will dissociate, okay? The only example. Other than that, all covalent compounds, as long as they're not in water, will not dissociate, at least not in water for the acids. Okay, so that is a polar covalent bond. How do we know? Because hydrogen and chloride are two different atoms. Okay, automatically polar covalent bond, and if we need to draw an arrow, it will go in the direction of the in the chloride, because chloride's a lot more electronegative. Hydrogen and hydrogen, it's a nonpolar. You got two hydrogens, two nonmetals. It is a nonpolar covalent bond because they're both the same element. We have chloride and carbon. We have that is a polar covalent bond. Something's making me sneeze here. Carbon and hydrogen, because we talked about that. They're both of the electronegativities are essentially the same. Therefore, we have a non-polar covalent bond. We're just talking about the bonds here, okay? Oxygen, oxygen, diatomic, same element, non-polar covalent. Potassium and oxygen. Obviously, we got an ionic bond here, okay? And then phosphorus and fluoride, we have a polar covalent bond. All right. So takeaways using the general formula of A and A, non-polar covalent bonds, A and B, polar covalent bonds, okay? The exception for the A and A is carbon, hydrogen. Now we could take it one more step, and we can draw the arrow from left to right for HCl, okay? Because chloride is a lot more electronegative than hydrogen. No arrow for sodium chloride because it's ionic, okay? No arrow for hydrogen because it's nonpolar. We have an arrow for carbon chloride going from carbon to the chloride because, again, chloride is the most electronegative. Nothing for carbon, hydrogen, nothing for oxygen, oxygen, nothing for potassium and oxygen because that's an ionic bond. And then finally, the last one, definitely going to the fluoride because fluoride is the most electronegative element, period. So of these examples, only 3 of them will require an arrow, okay? If we needed to take it further, let me reset it, it gives the impression it's going to sodium chloride. So from, hydrogen to chloride. All right. I didn't put the delta notation, but the point of the arrow represents the delta partial negative. So let's put it together with respect. We talked about the polar bonds, nonpolar bonds. Now, how does that apply with respect to the whole molecule? Okay. And because that's what we're looking for eventually. We want to analyze the type of bonds a molecule has, and then from that information, determine whether the molecule as a whole is polar or nonpolar. And so some things here to remember. When you have all nonpolar bonds, if you look at your molecule and the structure, and let's say, for example, you have something like, I don't know, hexane, which has 1, 2, 3, 4, 5, and 6, and everybody here is a hydrogen, so on and so forth, etc. Yes, we haven't talked about this, but I'm just trying to demonstrate here that we have nothing but carbon-carbon bonds, which are the same element, which makes it nonpolar, and we have carbon-hydrogen bonds, which are nonpolar. So this whole molecule, all nonpolar bonds, all nonpolar molecule, okay? Now, why is it important to know the overall polarity of the molecule? Because we're going to talk about what are called intermolecular forces. And these are forces that are involved molecules with each other. And the only way to assign what force a molecule has is to determine the polarity of that molecule. And this is how we do it, okay? The polarity of this molecule overall is nonpolar. Therefore, it would have a specific type of intermolecular force that we're going to get to. This is called the IMF chapter. All right, so when polar bonds do not cancel out, okay, then we have a polar molecule, which once we know that, we can assign a particular type of intermolecular force. And that's why, again, it's important to figure out the polarity of the molecule. Notice that the arrows here, which I said are vectors, if they go in an opposite direction, they cancel each other out. These do not cancel each other out because we have an arrow going to the bottom left and an arrow going to the bottom right. They're not canceling each other out. And the reason they do that is because that lone pair in the central atom has caused that bond angle to be much less than 120 degrees. If we had something, I'm going to say something like this. This is, we have polar bonds, and it'd be trigonal planar. Okay, 120 degrees here all the way around. Okay, the geometry of this is that all these bonds, and I'm going to designate them as follows. Okay, the arrow is going toward the boron. We have 3 polar bonds, but because of the geometry of this particular molecule, these guys, all 3 of them cancel each other out, okay? Mathematically, I can't demonstrate that here, but graphically, I'm showing you the arrows will cancel out. And what results is that this is a nonpolar molecule overall, even though they got 3 polar bonds. Another example is, let's say we got a carbon bonded with 4 chlorides. I'm going to try to draw it kind of 3-dimensionally if I can. These 2 chlorides with the solid line are on the plane of the screen. This wedge represents a chloride bond coming out of the screen. And then the hatch mark represents a chloride going to the back of the screen. You take a look at the geometry in the shapes table, it gives you a better picture. It's tetrahedral. Now, in all 4 cases here with respect to the bond, we have polar bonds. We got 4 polar bonds. Okay, going away from the carbon and toward the chloride. Okay. Now, again, because of the symmetry and the geometry of this molecule, we have a non-polar molecule. Even though we have 4 polar bonds, overall, that molecule is non-polar because all 4 bonds in this configuration cancel out. We have 3 polar bonds over here, and because of this geometry, they cancel out, and they also end up with a polar bond. Now, if I take that same species, this is called carbon tetrachloride, and I replace one of those chlorides with something else, doesn't make any difference. I'm going to replace it with hydrogen. Okay. I only have 3 polar bonds, but one of them is not. Those 3 do not cancel out because I replaced that one bond with something else. So the result is that I have a polar molecule because the 3 remaining polar bonds do not cancel out. In fact, if I were to replace that with, say, bromine, okay, Rick said every polar bond, there's 4 polar bonds, but because there's bromine, the magnitude would be different than the chlorides. The result would be, I got a polar molecule because there's a little bit of difference in 3 of those bonds don't cancel everybody out because the bromide has a different magnitude. All right, so I'm gonna put that back to hydrogen. And if I go around and I still replace another chloride with the hydrogen, still polar. I come around, replace a 3rd one, I still have a polar molecule because I got still one polar bond left over. It is not till I go around the horn, so to speak, and I replace the last one with hydrogen. The fact that I have all nonpolar bonds gives me a nonpolar species. Okay, so geometry has a big factor on the polarity of the molecule, a big factor. All right, so let me clear up this mess here. And this example was carbon dioxide. Now, how do I know about the geometry? This is where the Lewis dot structures come into play. That's where we all tie it in. Okay, we started up with the periodic table. We learned about the valence electrons. We learned about the Lewis dot structures for the atoms. And then we got the molecules put together. We're given a formula. And we can go add up the valence electrons and come up with a structure, okay, and the geometry to give us either sulfur dioxide example or carbon dioxide. And then we identify the polar bonds on that molecule, which if you look at carbon dioxide, there are 2 polar bonds, one to the right, one to the left. And of the same magnitude, so that arrow is the magnitude is the same because there's the carbon oxygen to the left, carbon oxygen to the right, but they're going in opposite directions. And that arrow, like I stated, is a vector, has magnitude and direction. All right, so it goes 5 units negative to the left, 5 units positive to the right. The net result is 0. And so the carbon dioxide is an example of another example of a molecule having polar bonds that cancel each other out. Therefore, overall, we have a nonpolar molecule. Okay. And the only way to determine that is to actually write the structure. Okay. Determine, because you could be given any molecule and asked, is this polar or nonpolar? But other than these 2 examples. And the only way to determine that would be to write the Lewis dot structures and then look at the polar bonds and see if they cancel out to answer that question. Okay. All right, so we talked about the methane, which had 4 nonpolar bonds here. We have hydrocarbon. That's the thing to remember. Anytime you see a molecule that is just carbon and hydrogen, I gave the previous example, I had 6 carbons, okay? We call those hydrocarbons. Those are generic it's a generic name for those type of compounds that are made up of nothing but carbon and hydrogen, hydrocarbons. Methane is a hydrocarbon. You have butane, which you use on your lighter, propane to cook your hamburger outside where you're grilling. All those are the A and E are hydrocarbons. Okay. All right. So PCl3, trichlorophosphorus, all have there's 3 polar bonds. Okay. Now you might say, well, wait a minute. Let's think about this for a second here. All right. Well, you just told me that if this was trigonal planar, that I should, due to the geometry, that this should be nonpolar. Okay. Because the geometry is this trigonal planar, that's the AB3 configuration. Okay, and in this case, all the B3 are all the same, so the geometry is such that they will cancel out. However, do I know that that is the correct geometry? I don't. So what I got to do is I find the Lewis dot structure. Okay, and what I end up doing and finding out is that, guess what? Without doing the Lewis dot structure, this is the actual structure that we come up with. We got a lone pair on the phosphorus. And so that's trigonopyramid. And we've got a lone pair sitting there, right? And so every time I said earlier, when you end up with a lone pair on that central atom, you're going to end up with a polar molecule, okay? And sure enough, here we got a polar molecule. Even though it's got 3 polar bonds, you got 3 polar bonds thinking that they will cancel each other out. Okay, they're not. And the only way I know that for sure is I got to do the Lewis dot structure to determine the geometry of that molecule. So it's overall polar. And then we talked at length about carbon dioxide. Obviously, 2 polar bonds, but they cancel each other out. Okay. All right, so you might want to try this. We did this already. We did ammonia and we did water. So you might try that. Other than that, guess what? We're down. We're done. Chapter 7. All right. Any questions about chapter 7? Okay. All right. Well, no questions. Let's talk about nomenclature. All right. So don't forget, I've added some resources to help you out, and we're going to talk about those here in a bit. But let's go through the chapter first. It's a pretty short chapter. You know, we might get it. We might get it done today. All right, chapter 7 done. So nomenclature, that is a big fancy word for name that compound. And I've been introducing that the names of the compounds that we've been making as we progress. I also direct you to the, I believe it's called StudyMate on the website that helps you out with respect to nomenclature, naming these compounds, okay? Now, the big thing to take away from nomenclature is this. Ionic compounds, metal, non-metal combinations, we do not use any prefixes. Okay, no prefixes. What do I mean by that? Let's do this. Let's do a quick one. This is the formula for calcium chloride. Okay, we'll talk about this more here in a bit. Calcium chloride. That's the name. Okay. There's 2 chlorides, so we don't call it calcium dichloride. It's simply calcium chloride. So for ionic compounds, no prefixes. Okay. Covalent compounds, yes, on the prefixes. Carbon, dioxide. That was CO, carbon monoxide, okay? Don't mix and match. That's the main point to get away, to take away from these two. One of the main points, we got a couple other ones coming up, but ionic compounds, no prefixes. Covalent compounds, yes on the prefixes, okay? Now, initially, this chapter deals with ionic compounds to begin with, and then we're going to slowly move into their covalent compounds and naming them. Now, the other thing too, the nonmetals in both ionic compounds and covalent compounds, the name is changed. Like oxygen, we said in ionic, it becomes oxide. Well, the name in covalent, like carbon dioxide, that oxide part remains, okay? So the oxide remains either if it's ionic or covalent. The sulfide, same scenario. Sodium sulfide versus carbon disulfide or some sort like that. That's the non-metal name remains the IDE versus ionic or covalent. All right, so we know that obviously we talked at length on the neutral atoms, and of course they're neutral because they have equal number of protons and electrons. We did mention this before earlier to be familiar with the first 20, but we're adding a couple more. But barium, Ba is barium, Co is cobalt, I is iodine, Cu is copper, Fe is iron, Pb is lead, Ag is mercury, Ag, which is sometimes confused with Au, Ag is silver. Okay, I think maybe the G kind of confuses. They think it's, some students think G is for gold. No, Ag is for silver. Au, Latin term aurum, is for gold. Zn is zinc. Now this one is, we can use this too. This is stannous, or it could be tin. Either one's acceptable, okay? You may be familiar with this. If you look at your toothpaste label, you might be brushing your teeth with stannous fluoride or sodium fluoride, but that is tin, is the alternative name. Either one will work, okay? Only for that one. Ag is silver, or Au is gold, not aurum, but gold, okay? Sn is the only one that you can use both the stannous or the tin, either one. Sr is strontium, and then we got Ni for nickel, Br for bromine, Cr for chrome. This can be Mn for manganese, can be confused with Mg for magnesium, okay? And then we got Cd for cadmium. And we'll be using more as we go along. We're not going to get into the F elements or anything like that. Or most of the metals are going to be these, and maybe a few more on the inner transition metals. All right, so ionic compounds, we're well versed now. We should be, right? We got an ionic compound metal versus a non-metal. Okay, we're again covalent compounds, combination of non-metals only. Okay, we got the monatomic ions, where we learned about these elements becoming ions, either cations or anions, depending whether they are metals or non-metals. So metals lose electrons, so they become cations. Non-metals gain electrons, so they become anions. Okay. Their respective charge we're familiar with, hopefully, and only for the A transition metals, because we know 100% of the time the charges for some of these. There's a question. Apologize. Yeah, we do have a lot of information to go over. Sorry, I just saw your comment there. Apologize. All right, so let's go to the infamous periodic table. Let me make sure I got the right one here. Okay, you may have seen my little table here marked up a little bit different. So you might want to mark yours up. Yeah. All right. We've been talking about charges and basically either going to have a positive charge or a negative charge. Now, when it comes to ionic compounds, that's not a problem when we talk about charges because we're familiar they've got a positive and negative. But when we talk about covalent compounds, it's not really true with respect to charges, you know. But they also gain or lost electrons in covalent format. So what we do is we utilize the term oxidation number, okay? And so oxidation number pertains to both ionic or covalent, whereas charge is more of a term used for ionic compounds, okay? And so the oxidation number of oxygen, for example, will always be a -2, be it in ionic or covalent. But it's not a full-fledged -2 if it's in carbon dioxide. It's just a partial charge because it's sharing those electrons, okay? Anyway, there's there's all the metals. Remember how we had defined what the metals were, is that stair step to help you out on the periodic table, okay? To the left of the stair step right here are the metals, except hydrogen. Remember, hydrogen is not a metal. Hydrogen is there because it has the same number of valence electrons as everybody in group 1, okay? All right, so everyone else is a metal. Now, every metal in group 1 has 1 valence electron. Okay. Every metal has a 1 valence electron. And so we know now, hopefully, that when all these metals become ionic, they will have a +1 charge 100% of the time. There are 6 metals listed there, okay? Everybody in group 2, starting with beryllium on down, everybody there has 2 valence electrons. They will lose those 2 valence electrons and end up with a +2 charge, 100% of the time. So now there's 6 more metals that you know their oxidation number 100% of the time. Okay, let me do this. And so everybody up here has a +1 charge. Everybody here has a +2 charge. So now you have 12 elements that you know 100% of the time their respective charge. It does not change, it's exact. Of the other metals, there's only 4 that exhibit the same property. Aluminum, always 100% of the time has a +3. Okay, so aluminum is right here, number 13. Zinc always has a +2. Silver, Ag, always has a +1 charge, oxidation number. And cadmium always has a +2. One way to kind of remember that is if I find aluminum, then I can just draw like a wedge going this way, go down 3 and then across 1, okay? So now I have 4 more. So of all the metals here, you know 100% of the time their oxidation number when they become ions, 100%. There's no question about it, that's it, okay? What that implies is that everybody else over here, everybody else, their oxidation number varies. There's different oxidation numbers for them, depending on the reaction conditions and so forth. For example, right here you see copper. Copper can exist as either a +2 when it loses 2 electrons, or a +1 when it loses 1 electron. So their oxidation number can vary from 1 to 2. Some of these metals can vary from Well, the range of oxidation numbers that these other metals I've kind of marked up with the dark pin vary from a +1 to a +9. Okay. And so there's a lot of ambiguity there if you're not careful of, oh, how do I know which one I'm talking about? So what we do is we use Roman numerals to distinguish between which ion we're working with. Therefore, copper, for example, if we're working with copper 2 +2, then we use the Roman numeral 2 to designate that as the copper 2. Copper 1 would be designated with Roman numeral 1. Okay, so that Roman numeral, not to be confused with the Roman numeral on top of the groups, that has nothing to do with the oxidation number of the other elements. They're variable. Okay, that Roman numeral deals only for that metal and what oxidation. And you need to be told what it is. So you'll be given copper 2, copper 3. You know, iron is another example. Iron could be iron 3, Roman numeral 3. Okay, or it could be iron 2, Roman numeral 2, meaning +2 or +3. Okay, and so for those 16, no Roman numerals because they're exact. For everybody else, we use Roman numerals to distinguish which oxidation number of that metal we're working with. Okay.
So on the nomenclature, we have to add that Roman numeral in there when writing the
Yes.
formula? Okay.
You are correct 100%. And so
Okay.
if you're talking about, let's say, we'll give some examples. We will say copper, write the name out, maybe Roman numeral 2, and just for argument's sake, we just say chloride. Okay. And so if I see a formula and that formula there, I'm sorry, I can read it. The formula there would be copper 2. The formula would be this. We're going to give you an example on how to figure that out, but that's the formula right there. And if you're given CuCl2, the name would be copper Roman numeral 2. Okay. Or it could be copper Roman numeral 1 if we're given CuCl, just one chloride. We're gonna go over how to figure that out. So when you write that name in your nomenclature exam, you can't forget the Roman numerals. If you're dealing with anyone in group 1, group 2, and those 4 I gave you, no Roman numerals. Okay, so we wouldn't say for say calcium chloride, we wouldn't say calcium 2 chloride. Because we know that calcium 2 by default, just by the nature of the beast, has a +2. It's an exact. Okay. Clear as mud, huh? Look at my paper here is all messed up on my screen. Let's see if we can clear it up a little bit. So that's what I do here, and that's why I got that marked up in that manner to kind of show you that you got 16. I call them the sweet 16. Sweet 16 element metals that you know the oxidation state 100% of the time. Okay, it's an exact number for that value for the oxidation state. That means everybody else metal wise varies, and you have to be given more information. Okay, and you can figure out. For example, let's do a couple of. Let me get the whiteboard up here. Okay, remember I stated, well, if not, I'll restate it. The number of cations plus the number of anions for 99% of the molecules we're working with must equal 0. Okay, so in other words, say the number of pluses must equal the number of plus the number of negatives equals 0. They cancel out. I got to have enough of each other to cancel out. So with that in mind, let's look at this species. If I were to write CuO, okay, the question would be, what is the oxidation number of copper? Okay, you're always going to know either the cation's charge, oxidation number, or the anion. Oxygen always has a -2, be it in ionic form or covalent form. Okay. And so what does that tell you that copper must be? If oxygen is a -2, what must copper be for it to equal 0? What do you think? What number must copper be so when it's combined with the -2 of oxygen, so those two come together to equal 0? What must they be?
+2.
You got it. So copper has to be a +2. So what does that tell you in this formulation here? That this is copper, Roman numeral 2 oxide. Okay, that means this copper is a +2 oxidation state. Now, if I were to write copper chloride, again, I don't know which copper it is because copper is not part of the 16. So I don't know for sure what oxidation number would be. But what I do know about the chlorides, the chlorides are always equal 1. All the halides equal -1, I should say. So what does that tell you that copper must be here under these conditions?
+1.
You got it. So it's got to be +1 in order to equal 0. So that tells you that this is copper, Roman numeral 1 oxide. Now, I've been fixing it as we go along, but crazy canvas, whether you put a space after the Roman numerals or not, I think Canvas is set up to accept space as correct. But if you put a space, it's one or the other, either with a space or not a space. Canvas correct is wrong. It counts it as wrong. Let me know. I will correct it. I'll give you your points. There's no question. It doesn't make a difference whether there's a space after copper or not. What's important that you understand it's Roman numeral 1. That's the main part. All right. So
Would that be copper chloride?
what's that? This. The name. Oh, thank you. I was thinking of the oxide up here. Thank you very much. All right, copper chloride. Yeah, good old copper. You know, there's 2 types of copper. There's copper 1 and there's copper 2. And the old nomenclature, they will use cupric and cuprous, which is quite ambiguous. And now there's an organization, worldwide organization, IUPAC, the international organization that deals with nomenclature. And so every chemical that's out there has a very specific name. And so whether you're a scientist here in Arizona or on the other side of the world, everybody understands what compound it is. I was in the lab one time where I had a Japanese scientist, one from Lebanon, myself. Our communication skills were, not the best with each other. We were on the board writing down equations, and we understood what was going on as far as what we wanted to do with the chemistry. So it is a language, kind of, sort of. And we're right now learning the alphabet and putting it together to write words. Now, as I'm going to say, there's copper 1, copper 2. Obviously, we got copper 0, which is the element, okay? 3 forms of copper. The only difference is the loss of electron. So when you're taking, like you need copper in your diet or iron, you're not messing with the element. You're messing with the ion. You're ingesting the ion. Both very distinct properties, the copper 1 and copper 2. One has a green color, one has a very beautiful blue color. In fact, growing up in Arizona and Superior, which is a mining community, there's a lagoon we used to play in, which we weren't supposed to, but we did. There used to be some beautiful blue water, sort of like what's behind here. And we used to think, wow, that's cool. Turns out it's a cyanide compound. I didn't know this until I became a chemist, I was playing in the cyanide copper compound. And anyway, I'm surprised I'm still alive. But I have to say, once I learned about that, I did went and researched health issues with respect to mining communities around here, like Superior, Globe, Miami, Morenci, Kearney. And on a per capita basis, by and large, there's a higher percentage of cancers in these small mining communities compared to the rest of the US. So a lot of this stuff, a lot of these heavy metals, and it's just copper, and there's other heavy metals out there and so forth. So anyway, little side note. Let's go back to the main. All right, so the polyatomic ions, I've talked about these. They're on your periodic table in the bottom left corner. These are our polyatomic ions with their own specific name. They are packets, units that we keep together. And if we need to add more, we use parentheses, okay? Now, I mentioned to you what I mean by oxidation state. It's just a fancy word for the charge. And we use oxidation state because, again, the difference between ionic compounds and covalent compounds. Covalent compounds, we're not really talking about a full charge. We're talking about a partial. So oxidation number, oxidation state encompasses everybody, all right? We know that all elements have a zero oxidation number. Why? Because we have equal number of protons and equal number of electrons. They cancel each other out, okay? And we also know, hopefully by now, that these elements, depending on what type of elements, will either lose or gain electrons to form ions. And some elements, which I just showed you, have a fixed charge. There's only one possibility for their charge. I should say only one at this time. Doesn't mean it doesn't change, next week when new data is found out. But right now there's 16 of them with a fixed charge. And that will help you because sometimes the anion, earlier I was showing you what is the charge for copper. We knew what the anion charge is, but it could be reversed. It could be a fixed charge metal hooked up with an anion. You don't know what the charge is, but you can calculate it because you know number of cations plus the number of anions must equal 0. So one or the other. It's it's two variables there, 3 variables. You're going to always know 2 of those 3 variables. Okay, you calculate them. All the other ones have, all the other 16, other than the 16, have a variable charge, and therefore we use the Roman numeral naming, capital I's, not the lowercase I. Okay. We know this, we talked at length about it, about the different groups and the metals that are in these groups. They have their respective oxidation number of +1, +2, +3, based on their group number that they're in. Zinc and cadmium is always a +2, silver always a +1, and all the other metals. So there's 16 metals that their oxidation number 100%, they're constant, they're exact. That means all of the other metals can vary, and they're going to vary from anywhere from a +1 to a +9, depending on the conditions. So we utilize the Roman numerals as that we discussed earlier. So that's this example here with copper 2. You have copper 2 in Roman numerals that represents the charge oxidation number on that metal. Okay, has nothing to do with what follows after the Roman numeral, only with that metal. Iron 3 is designated as Roman numeral 3, all uppercase. And then we got lead 4, was Roman numeral 4. Okay. You're familiar, hopefully by now, about the anions. Anions have a negative charge. And so if we look at the periodic table, which I should have done here, I didn't do that, but let me go back there real quick. Okay, we told you about the charges on the metals and their exact numbers, +1, okay, +1, +2, and then these that, that we wrote there, the silver, so on and so forth, okay? Now, with respect to the nonmetals, we're talking most of the nitrogen, phosphorus, and then most of these right here, and then going down to here, okay? So these guys will have a -3, -2, and -1 respectively, okay? And so those guys by themselves, notice that those are the elements by themselves have that charge. Now, a lot of these elements, the anions, will bond with oxygen, like the sulfate. You got sulfur down here that will bond with oxygen. That's totally different ball game. Okay, when we're talking the polyatomic ions, we're talking about the monatomic ions up there, -3, -2, and -1 respectively. Okay. -3, -2, etc. And then obviously, as we know, 0 for the noble gases, right? All right, so ionic compounds. We're going to talk about ionic compounds, the combination of metals and nonmetals. We're going to begin by learning names, and then eventually, once we learn the names, because we got to go both directions. We're given the names, you get the formula, give the formula, give the name, okay? Now, the sum of all charges must equal 0. That's a very general formula, okay? Now, I like to expand on this definition here. The sum of the oxidation numbers, well, since we're talking ionic charges, must equal the 99% of the time to 0, but in parentheses, you can put the charge of the compound. And I'll give you an example of what I mean. Let's take that polyatomic ion, which was sulfate, okay? We know 100% of the time the oxygen each have a -2 charge, right? So we can calculate the oxidation number of sulfur the way it's bonded here. And we do that by using this equation, but I've incorporated the charge of the compound because the charge of the compound is -2. So I can say sulfur plus, we got 4 oxygens and each one's a -2 is equal to -2. See, I like the charge of the compound because it encompasses these ions that you can use. Yes, 99% of the time they're 0, but sometimes they're not. And I do know in your homework, there are examples of ions like so, and they want you to calculate the charges of the central atom. All right. And you can, depending on the polyatomic ion, have fractional charges. These are charges that are spread out amongst, 2 or more central atoms. All right, so that's something to remember to help you with that homework. So if I take the general formula and I set it up as follows, what I got here is sulfur -8 is equal to -2. A real simple algebraic equation, okay, nothing complicated. I'm solving for sulfur, okay? And so sulfur now is 8 minus 2 is equal to +6. So the oxidation number of sulfur in the sulfate ion is equal to a +6 oxidation state, okay? And that's why I like the general formula that encompasses everything. So now I can incorporate the charge on any species I get thrown with to calculate, okay? All right, so just keep that in mind. All right, we talked at length of polyatomic ions. We need more than one. We're going to use a parentheses. All right, so compounds, once we put them together, unless we start talking about putting together polyatomic ions, but for compounds, they got to be neutral. So we got to add enough cations and enough anions to equal 0. Okay, so let's take this example. Let's say combine sodium and nitrogen. And normally what they do is they throw you just the element. Well, we're not putting elements together. We are putting ions together. So we have to take the element that is given, find its oxidation number, okay? And we know that sodium has a +1 because it is in group 1, has 1 valence electron. When it becomes an ion, it'll have a +2. Nitrogen is in group 5. When it becomes an ion, it's a nonmetal, it will pick up 3 electrons. So nitrogen will have an, oh, there's a way there with that. Nitrogen will have a -3 charge oxidation number. And I'm going to interchange charges because we are dealing with ionic compounds first. All right, but I'm trying to maintain the oxidation number naming. Also, nitrogen now becomes name-wise nitride. Okay, now keeping this in mind up here, I need to add enough of each to cancel out each other. So I need to add at least 3 sodium. So what I do is I can, in this stage, and I put everything, let me regroup first. Put everything into ionic form first before you put them together. This is, again, a systematic approach. Eventually, yes, as you become more familiar with them, you can bypass that step. But if you, until that time, put them all in ionic form, and then put down how many of each you need to cancel out each other. So obviously, I need 3 positive to cancel the -3 of the nitrite. That 3 becomes the subscript. And so my formula is now Na3N. Okay, sodium nitrite will be the name. Notice for the metal, that doesn't change name-wise. It is the anion that changes its name. Okay. All right, so there is our formula subscript, and that is the ratio of the 2 atoms coming together to make that particular compound. So sodium nitride is the name of that. All right, let's do some more. Okay, so you're given the elements. First step, convert the elements to the ions. We know we just did sodium, so we know it's a +1, okay? Sulfur is in group 6. It's a nonmetal. So when it becomes an ion, it would have a -2 oxidation number, okay? Furthermore, its name becomes sulfide. We need 2. Now, I know some people go ahead and put that subscript right there just to tell you, all right? It makes me worry. I just put a 2 there in front of it, coefficient, and just alerts me that coefficient will be the subscript when I put them together to write the formula. Okay, so the formula for this one would be Na subscript 2. There are 2 sodiums for every sulfide. Okay. Again, we're given the elements. Magnesium, we got to find it in our product table. And we know it's in group 2, so it would be a +2 oxidation number. Oxygen, like sulfur, is in group 6. When it becomes oxidized, or excuse me, it becomes ionized, become an ion, it's a -2. In this case, I got a +2 and a -2. I can simply put them together as a 1-to-1 ratio. Okay, and so its formula is MgO. Okay, MgO. All right, let's put together potassium and phosphorus. Well, potassium, like sodium, is in group 1. So ionic form of potassium is a +1. Phosphide, or phosphorus, excuse me, jumped ahead. excuse me, oxygen now becomes oxide. Name phosphorus is in group 5, okay? Group 5. So it will have a -3 oxidation number. That means I need 3 potassium to cancel the -3 of the phosphorus that now becomes phosphide. Okay. And our formula then becomes K subscript 2, 3 phosphide. Okay, a little more challenging. Let me clear this up, but let's think it through, okay? Let's clear this up a little bit. We'll come back and get the names, write the names here in a bit. All right, so we got calcium. We've looked for calcium. We know it's in group 2, so it becomes the +2 oxidation number as an ion. Nitrogen, okay, like phosphorus, is in group 5, so it becomes a -3 ion, and that becomes nitride, name-wise. So I write that down because I keep track of it, because I might have to write the name for that compound, and we will once we're all done. All right. So now it's not as straightforward as the other 3 examples, right? And the other 3 essentially, okay, I need 2 to 1, 1 to 1, 3 to 1, respectively. Here, I got a +2 and a -3, and I got to put them together such that their charges equal 0. But I got a little bit of a problem, right? I got a 2 and a 3. So what do I got to do? Well, I'll give you a hint. What if I needed to add this fraction, 1/2 plus 1/3? How do I go about adding that fraction? What do I need to do?
Find a common denominator.
You got it. I got to find a common denominator, and normally, most of the time, I could just multiply the denominator. So the common denominator here would be 6, right? So if I multiply this one by 3, and then the other one by 2, I got a common denominator. So I got 3, 6 plus 2, 6. I'm good to go, right? Well, I get the similar scenario here. What would be the common denominator between a +2 and a -3? Obviously 6, right? So what I need to do is I need to multiply a +2 with a number to give me a 6, in this case, a +6. And then for the nitride, I need to get to a -6. So I need to multiply that by some number to give me -6, and that's a 2. So these numbers become the subscript for that compound. So the formula would be calcium subscript 3, nitride 2, okay? And our common denominator, as you stated, is +6. So I got +6. I got +6 from the calcium because I got three calcium, and each one contributes a +2. And then nitride, each one contributes a -3. So I got 2 of them. All right. Now notice something interesting. Notice how the subscript for the anion was the oxidation number for the cation. And notice the subscript for the cation is the oxidation number for the anion. So maybe that might help you out a little bit, okay? If you forget, you may just cross the numbers. So its formula becomes as follows: Ca3N2, or subscript, okay? And then aluminum and chlorides. Well, we know that aluminum's in group 3, so it would have a +3 charge. And we know that the chlorides are in group 7, and chlorine's in group 7, and when it becomes chloride, it would have a -1 charge, oxidation number. And so I need 3 chlorides to balance the +3 of the aluminum ion. And so our formula would be AlCl subscript 3. Okay. And then zinc, break it down. Zinc is one of those metals. It's one of the D elements. Remember those, but it's one of the sweet 16. And so it's got a +2 oxidation number all the time. And iodine, just like the chloride, has a -1, and therefore we only need 2 of those. We balance the +2 of zinc. And so our formula now becomes ZnI subscript 2. And we got this guy. All right. What this tells us, remember, is that Roman numeral tells us the oxidation state of the copper. And so that says we write the ions first so we can put them together correctly. So that's Cu + 2. Now the oxygens are in group 6, right? Oxygens in group 6. When it becomes an oxide, it's what? It's a -2. Okay, so that becomes oxide. So now we can put those two together as a 1-to-1 ratio. And that is the formula for copper to oxide. Let me write the names here. Oh, let me do one more, sorry. We got lead, Roman numeral 4, which tells us that that is a +4 oxidation number. We continue to have oxygen, which is a -2, right? So we need 2 of them. We need 2 -2s to cancel out the +4 of the lead. And so our formula now becomes as follows. Now, so let me clear this up and let's do the names real quick. And so the first one was sodium. And then sulfur became sulfide. Okay. We got magnesium. Oxygen became oxide. Then we have potassium. Phosphide. Okay. And then we got calcium. Nitride. Aluminum. Chloride. Zinc. Oh, zinc iodide. Okay. All right. Now, notice all these metals up front are the first 6. We did not use any prefixes. Okay. No, like calcium, like this one. We didn't say tricalcium nitride, simply calcium nitride. No prefixes in ionic compounds. We also did not use any Roman numerals for these metals, 1 through 6. Why? Because they are part of the 16, the good old sweet 16. They're exact constant oxidation numbers, therefore do not require Roman numerals. Unlike the next one, which is copper 2, okay? It is a variable oxidation number, and that's why we have to be given the oxidation number if we are given these 2 elements to make a formula. So its name would be simply copper, Roman numeral 2, and then the oxygen is oxide. And then we got lead. Don't forget the Roman numeral, oxide again. Okay. All right, so with that being said, keep this in mind. You can take this sodium and hook it up with the oxide, the phosphide, the nitride, obviously the chloride, the iodide, okay? You can do the same with magnesium and do a mix and match. Magnesium with the sulfide, magnesium with the phosphide, et cetera, et cetera. And so you can see you're starting to build up a database. You probably had maybe at this time with all the metals we have so far, you can probably put together a 400 or 500 database of compounds. Okay. All right. So we will continue with this chapter next Friday, because I noticed the time here. I went a little bit over. All right, and I think the exam is not this week, it's the week after. So we'll be done with this chapter and the other one, so we'll give you another week to get ready. Right.